Hello, everyone. My name is Octavio Vite-Sanchez. I'm a PhD student at the NRS. My supervisor and co-supervisor is Pierre Simon Ross from the NRS also, and Patrick Mercier Langebrand from the Geological Survey of Canada. So following with the BMS thematic project, this is the project 1B, and I'm going to talk about the Mafic volcanic rocks of the Blake River Group, geochemistry, petrogenesis, and relation with BMS deposits. So we've been seeing a lot of this map today and yesterday and the whole talks, but just to mention that the BTV Greenstone Belt has been divided into 7 episodes, as you must heard. So this is the episodes here that represent the colors on the map. So this assemblages has been mainly defined on H's and lithologies, plus some geochemistry. And one thing that it's interesting here in the BTV Greenstone Belt is that the BMS deposits tend to occur in certain assemblages. For example, here in this graphic from Moniki, we can see how the low row, Kidmore Row and Blake River tend to host the majority of the BMS deposits. So we want to know what is this going on, and we want to address that from the point of view of the geochemistry. So for that, we need to know the geochemical evolution of each volcanic assemblages, but sadly it's not well known in detail. So it's difficult trying to link those things in terms of geochemistry and BMS fertility. So that's one of our aims for this project. And we want to put attention for the subalkaline volcanic rocks that goes from ultramafic to felsic. So our methods for this project is going to be assemble a large lithogeochemical database for subalkaline volcanic rocks, and for each subalkaline or for each volcanic assemblage, we want to classify the rocks. We want to create groups, a cluster of geochemical groups, and we want to document the petrology and define the petrogenetic evolution. And with that, we want to know why certain assemblages has more this BMS endowment and why the others not, and what are those geochemical signatures that are related to the BMS deposits that could help for example, to vector for exploration, at least for a regional scale. So just to explain a little bit, this talk is about the Blake River Group. The Blake River assemblage is bigger than that, so we are only going to focus in the Blake River Group that is marked here in green in this rectangle. So here in the top, I showed you guys a simple geological map from the Blake River Group, showing you we can see how the vast majority of the rocks is from mafic volcanics. We also have felsics and intrusive rocks. We can see here how the BMS deposits are located in the Blake River Group. There is a lot of work that has been done in the felsic rocks, because normally it's there where you are found in the BMS deposits, but we now want to look into the mafic volcanic rocks. That's where this work is going to be. So in the bottom, I showed you the subdivisions from the Blake River Group. In the left, you have the Ontario side. You only have two formations, the lower Blake River and the upper Blake River, and from the Quebec side, we have 9 different formations. So this is all the samples that we gather for database. We have to screen several samples, because we are looking volcanic rocks that has a complete or certain mandatory elements that has, for example, rare earth elements or immobile elements that could be helpful for the petrogenesis studies and geochemistry. So at the end, we have close to 2,000 samples. So we have different attempts to achieve to our final grouping. So I'm going to talk to you about the 3 different attempts that we did. So our initial attempt was to do a manual subdivision, a manual, based on the Winchester and Floyd 77, just to subdivide between felsic and mafic. And within the mafic, trying to subdivide between andesites and bosons. So to create our geochemical groups in terms of magmatic affinity, we use Rosa-Bedard, and we have an example of the plot on the right. So we use this diagonal lines that that are already provided in this plot, and we try to subdivide that in terms of toleric, transitional, or calculant, but that produce a continuum of data with no natural cluster, let's say, and we try to validate our groups in the spider diagram just to see their signatures. They overlap. We have some overlapping between groups, and when we plot that on the map, it was really difficult to follow or to interpret. So we move on to another attempt. So for this, we use computational methods. We're trying to use clustering. We're trying to use principal component analysis. We also use linear discriminant analysis, but we tend to have the same problems, but maybe because we don't know what we were doing at some stages, so maybe that's why it causes several problems for this type of method. So we move on to another, and we finally adopt a more petrological approach that was based on three main processes. So the first one was magma fractionation. For that, we use zirconium titanium ratio, and then we use the mantle sources variation. For that, we use niobium ytterbium, and lastly, we use the crustal contamination proxy, which is the thorium ytterbium. So if you merge these last two, you end up with the Pierce 2008. So this is how we start our first order grouping. As I mentioned, we use Winchester and Floyd at the beginning, but we end up with the Pierce 96, which is based on the Winchester and Floyd. But actually, Pierce works better in terms to work better for us to trying to subdivide between mafic and felsic, and then subdividing between andesites and basalts. So our proportions between basalts and andesites, it's normally 1:3. And and another thing that we did was trying when you plot the raw earth elements, the ratios of the heavy against the light one, you normally have a continuum of data points with a normal this positive slope, very gentle. That goes normally towards a more felsic compositions, but we have some samples that really has this high ratio of gadolinium and ytterbium, and we take the samples into another group, but we are not going to deal with this group in this presentation. We don't have enough time, so we plan to deal with this for the paper. So then, just to explain you just from Pierce 2008 plot, I think maybe you heard about this plot, and several persons mentioned this, but to some of those persons that haven't heard, is just to explain you just a little bit. Pierce originally used this plot to trying to describe the mid-ocean rich basalts, trying to see their characteristic, and he discovered that you could have more depleted sources and more enrichment sources, and even you could have these YB compositions. So he marked this this gray line to call it the mod YB array, and even if you plot samples that has another composition, for example, from the volcanic array, they could plot over here. So now that I mentioned the volcanic array, one of the processes that affect this plot is the subduction processes. So if you're having subduction processes, they normally tend to plot just parallel to the MORP OYB array. And you can see it here with one just example from the Mariana arc in these white squares over here. They plot they are just shifted from the MORP OYB array, but they are parallel to that array. Another process that could affect or this plot is the AFC processes. So if you have a parental magma that comes from this array, and this magma is affected by some contaminant, for example, here we have the Archean crust, this contaminant could shift your composition, and even you can model that with the equations from De Paolo. and you can generate these curves just trying to see if you have more assimilation, then your composition is going to be closer to your assimilant. So when we plot our data of the Blake River group in this Pierce 2008, we tend to have the overall data. We tend to have this oblique tendency in our data, that you can observe that you have a mantle composition, this more YB, that goes from a depleted source to a more enriched source. And you can see here the primitive mantle. So we start thinking in the literature, when you have these oblique trends in this plot, they call it, or they associate that to a AFC process, where you have a contaminant affecting your magmas. So there are several persons that mention this. I put you some authors that mention that they initially start observing these processes of contamination in comatites, but there are also some authors that mention this for the Blake River group, for example, the inheritance of in zircons. Some authors mention that, and also you could see that in the radiogenic isotopes and trace elements in zircons, for example. So we believe that an AFC process is happening here, and we model that. So we take several mantle sources along of this range, just to see what happened if you have an assimilant. And first we use their key and cross average, and we have here 3 different colors just to show you what is the behavior in terms of the ratio of assimilation. Greens means where you have the lowest ratio of assimilation, and the blue ones when you have this highest ratio of assimilation. And the literature, they normally use the 0.3, so we also put it there. Oh, just to mention, their key and cross was doing something good here. Their groups try to cover maybe the most part of our data, but we are missing some of them just over here in this upper part. So we use another source that is more, let's say, more local. And for that, we use the Southeast Superior TTG average from MOL 2021, sorry. And we like more this their behavior of the corpse in this plot. So with that in mind, we use these corpse just to try to make a subdivision here in the same plot. And I'm going to show you how we did that. So this is the same plot, and using this corpse and the level of contamination, we distinguish 2 sources and 3 levels of contamination. So we distinguish a source that is more depleted and the other one that is more enriched. The line between these 2 them was put it there manually, trying to follow the something parallel to the corpse and something more close to the primitive mantle. Then we take a small cluster of samples like around the line, just to trying to validate how they are, their signatures. They look more enrichment and more depleted. So so we make the line over there. We believe that's the line of subdivision between these 2 sources. But then we create these other 2 groups that are the equivalents of these 2 sources, but that they are contaminated. And these 2 groups go from 10% to 70% of contamination. So maybe you might ask why is between that. Because when you have at least at 70% of contamination, you can still distinguish what is their source, if their source is like more depleted or more enrichment. So beyond 17% of contamination, then you tend to see that the signature of these rocks are more related to the contaminant. So we put this here in another, for example, tectonic discrimination from Agrawal, just to see what is their behavior, and we like to see how rocks that has the more original magmas, let's say, and their equivalence contaminant, they still remain in the more array, and how the contaminated will be shifted to this another array that in this case is the island arc basalt due to the TTE contaminant. So this is the spider plots. We can see here for the more depleted source, they have this behavior, this flat line that is typical from these depleted sources, low concentration, symptorium. And when you're starting to see their contaminant equivalence, we start seeing here this small influence from the contaminant, which is the TTG. So we start seeing here more concentration, symptorium. The black line means the average of the whole group. And then when you see the enriched source, this signature is more typical from them. We have low concentration, symptorium, and enrichment in laboratory elements. So that's typical from this type of signatures. And then you see the contaminant equivalent. You start seeing this the influence of the contaminant. And then when you see the contaminated group, then these signatures are more related to the contaminant. And when you in the case of the andesites, they have a similar behavior of their basaltic analogues. But they have, in general, they are more enriched enrichment in the whole trace elements, and you have this titanium anomaly because the titaniums tend to be more compatible when you have more evolved magmas. But they tend to be similar to the basaltic analogues. So we like their behavior of the spider diagrams that progressively change with each group. So this is the spatial distribution of our groups in the Blake River group. If we saw the Ontario site, we can see how where we only have two formations, which is the lower and the upper. Just by eyes, we can see how the lower formation is more influenced by this depleted source, and how the upper Blake River group is more influenced by this contaminated group. The Ebicool formation is the continuation of the lower Blake River group, and we still have the same signatures, and is the same, for example, for the Renaud of Fresnel formation. So it tends to be more messy, but we are going to see the proportion in each formation in the next slides. But we tend to see some clusters between the groups. So, and yes, that's for taus. Here, how is the proportion between andesites and basalts in each formation that is present in the Blake River group. So, just to follow these plots here, we subdivide the source, and we put it here. This purple color means the depleted source. The red means the more enriched source, and this green is the contaminated group. We also include the high gadolinium group. So for in here, as I mentioned, we can see how the lower and upper Blake River are differentiated. We can see how in the Ebicool formation we only have this source. But for the case, I mean, it's going into the formation that are more that has this mineralization, this important mineralization. For example, we can see how in Noranda we have this majority in the more enriched source, and how in the Busquet you have this big influence of the contaminated group. So here, we are not sure. We don't have a good sampling there, so we put it just like that because we are not sure if we have a good sampling going on over there. So here in the bottom, we just see the contamination influence. So for this, in this purple, we put these sources, those sources that are not contaminated. Then in yellow, we put this equivalence of contamination from these two. And yes, and the contaminated group, we just leave it like that. So if we contrast, for example, the Ebicool with this Noranda and Busquet formation, we can see how for the Noranda Busquet, we almost has nothing of sources that has no contamination. So that's some interesting relation that that we could observe in terms of the geochemistry of the geochemistry groups that we have been doing. So now here we have some zoom in the Noranda camp. We're going to see only Noranda because we don't have too much time. So here the volcanic stratigraphy, we have a homoclinal here going on with the base going on here that and the joining direction go to the northeast. So we can make a profile there just to see what's going on with our volcanic or for geochemical groups, because we tend to see here how some volcanic strata tend to follow our geochemical groups. For example, here in the bottom, another volcanic strata that is following our geochemical groups, when then we have here some contamination, and in the top we have some more depleted source. So we put it here in these profiles, and we also put the BMS deposits, and we can see, for example, some relationships here where you have more fractionation in your rocks, then you still then you are that's where you are having your BMS deposits going on here. And another relationship that is interesting to see is when you have this episode of magmatic activity, this magma is generating that has no contamination, then you are your BMS deposits going on here. And if you saw, for example, here for these other BMS deposits, for example, Amulet and Mirrenbach, you have it here surrounding of this type of, with these rocks and with these signatures. So that's some interesting relationships. So our conclusions for the Blake River mafic magmas is that they have, or they were derived from variable mantle sources that range from depleted to enriched sources. So the depleted source is more dominant here for the Blake River group, and is the crustal contamination here in the Blake River group plays an important but variable role for the magma evolution. And we can see how these geochemical groups can give us some ideas from the volcanic cycles that we could have, and those cycles or periods where we have magmas with high degrees of crustal assimilation seems to be related with BMS deposits. So mafic rocks are also important to assess this BMS fertility. So our next steps is to submit this paper on from the mafic volcanic rocks in the Blake River group. Then we want to take a look for the felsic rocks in this same area. So at the end of this year, we want to work for the geochemistry in the Pacaut and the oldest assemblages in the Blake River, because last year we went to the field and then we bring some samples from these oldest assemblages. And then the next year we want to work for the rest of the assemblages in the VTV and trying to link this geochemical signature that we could found with this BMS deposit. So that's everything for me. Thank you.
Great, thank you very much. We have time for one quick question.
I have a long question. Can I try and make it quick?
I know you do well. Go ahead, Mike.
Well, I have three questions, so you can take your pick. So
Yeah.
Zirconium to titanium is a bit of a mixed bag because it's affected by oxides, the degree of fractionation. It's also, as you've shown, affected by contamination. Probably the most important question is, did you try looking at data density plots? Because it looked to me like you might have had some completely separate, like two separate clusters in the Pierce diagram that sort of look like that, and then a bunch of stuff that trailed up. And then the third question would be is, what if your parental magma was more magnesian than a basalt? What if you started with a komatiite, for example? That would change the amount of AFC, and but would not necessarily change the location on some of the plots, but it would remove some of the objection about there being too much fractionation for it to still be, you know, a mafic or a an intermediate magma.
Okay, yeah, I mean, first with the zirconium titanium, yeah, I mean, we don't try that method that you mentioned. We were trying to look something that help us to subdivide mafic rocks. So the first 96 was the one important, or the plot that helped us to that. So yeah, but maybe we can put the chance to look into that. So I think the other question was about the AFC trends in the piers. So yeah, we have this another trend that is going on here in the Blake Weaver group, and yes, that's why this is the other group that I mentioned, the high gadolinium ytterbium group, that is going on here in the Blake Weaver group, and we put it in another group, and honestly, we don't have the time to try to see what is going on, what are the processes that are affecting these rocks, but we are going to talk for sure of this group.
That's not what I meant. I thought there were two clusters in there. There was two that were parallel to the mantle array. It just looked like it could be, and the way to tease that out would be to plot data densities. And
okay, yeah.
rather than just have so many points plotting on top of each other.
Okay, yeah. Yeah, I mean, we believe that it's a continuum of data, but yeah, that could be for sure. We will need to take a look, but we believe there's an AFC process going on here. And yeah, if you plot the comatites, yeah, for sure they are close to our data that is more that has more closer composition to the mantle.
Yeah, and if you look at, if you remember Klaus's presentation, he showed that you can fractionate those down all the way to mafic rocks, and so you know, if you then contaminate them at the same time, which you don't do in a differentiated lava flow, then you can end up with some things that are still more mafic but more contaminated, if you know what I mean, rather than just starting with basalt.
Okay.
All right, guys. Thanks. We're going to move on. Thanks for the presentation, Octavio.